Our work so far is focused on cryptography for achieving privacy. That's what symmetric encryption tries to do. We're now going to move on to other things like achieving integrity and authenticity. And for that, we're first going to step back and remember that as per the structural paradigms we discussed about a Lego approach for building cryptographic primitives, there's atomic or lower level things and higher level things. Block ciphers were one of the examples of these atomic primitives, and then we built symmetric encryption on top of that. So we're now going to go back and look at a second atomic or low-level primitive, which is hash functions. These are very nice, elegant objects, very simple to specify and talk about, but yet fairly subtle in terms of security. And our discussion will be largely empirical. And once we have them, we'll be in a better position to define and achieve various integrity goals. Perhaps what's made hash functions most common in the news these days or in popular understanding is the bad news. This is the announcement just a couple of years back that the SHA-1 hash function was broken. We'll get to that story somewhat later and see how it fits in with things here. So, hash functions, cryptographers design lots of things they call hash functions. The first series of them was the MD series. It had a MD4 function and MD5, MD6, with MD5 the most popular. Then there was what's now called the SHA-2 series, and the SHA-1 function we just briefly looked at was one of those. And there's several others in this series, where for these others, the number at the end denotes the number of output bits. Right now, SHA-256 and 512 are popular in-use hash functions. And the most modern family is SHA-3. These have emerged from a recent competition. And again, the number after the hyphen is the number of output bits. So what are these things trying to do? Well, they're designed to have as primary purpose collision resistance. This means that you can map long inputs to short outputs, and yet it would be difficult for an adversary to find two inputs with the same output. But in fact, their usages and properties seem to go way beyond this. A hash function is often treated like a magic wand. We would discuss it being what's called a random oracle. We'll maybe touch on that a little bit, but much more in the graduate class. Important uses of hash function include certificates. So how you know that some website that you're connecting with over the internet is who they claim to be is established through what's called a digital certificate. And an important part of that certificate is the use of a hash function, itself a part of a signature scheme. Bitcoin uses hash functions for proofs of work. There are data authentication mechanisms used in the TLS protocol that rely on hash functions. So many uses in many places this thing arises. It's perhaps a little ironic that the acronym SHA stands for Secure Hash Algorithm, given the slide we just saw about its demise. Maybe naming will change conventions. With regard to security, in some ways, hash functions are a little easier and simpler than many other things we've seen. When you have some function h, it has some domain, let's say, and it has a range, which is the set of all strings of some fixed length, here n, and you think of the domain as being large compared to the range. A collision for such a function is defined as a pair of inputs, 2 points in the domain, such that the output of the function on them is the same. So simple. To make it non-trivial, of course, these two inputs should be different. Otherwise, of course, the output is the same. Now we consider the task of identifying or finding such collisions or asking if they exist. And as long as the domain has a size that's larger than the size of the range, collisions will mathematically exist. This is something that in some sense is quite obvious. Mathematicians, however, call it something is called the pigeonhole principle, which states that if you have n boxes and n plus 1 pigeons to be put into them, some box will have 2 or more pigeons. So you can see that with hash function collisions by saying, suppose I had a domain of size 3 and a range of size 2, and I'm trying to build a hash function. Well, if my function tries to avoid collisions, what can it do? It can send the first input somewhere, second input somewhere else, and then you're stuck. There's nowhere the third input can go that doesn't result in a collision. Okay? And so that is always going to happen when there are more inputs than outputs. The intriguing cryptographic twist on this, which makes collision-resistant hashing possible, is that even though collisions exist mathematically, that doesn't mean they're easy to find. If I give you a description of the function, it could still be that if I then ask you to actually hand me a collision, a pair of points x1 and x2 such that the function output is the same on them, it's not easy to do that. So we're going to formalize that idea, and having done so many formalizations in the past, we can move pretty quickly to the actual games. It's helpful also that this definition is actually significantly easier than some we've seen before, so should be hopefully quicker to assimilate. Although in the past slide we talked about a particular function, the formalization applies to a family. We know what a family of functions is. We've seen it a few times. Block ciphers, PRFs are examples, but there are many other examples. And all it means is that it's a two-input function. The first input from a space or set called keys that then functions as a key, and the second input from some other input set D and outputs in some range R. Also remember that if we make a particular choice K of the key, then we define from it a function h sub k that maps the domain D to R. What does it do? It just applies the big function h on the two arguments k and x. But the idea behind this is that we usually think of k as fixed, and then we think of computing this for different values of x. Okay, so we're handed such a family, and we want to define a metric of security corresponding to the ability of an adversary to find collisions. So the game is called CR for collision resistance. It's subscripted by H because we're measuring security of H. In the initialized procedure, a key is drawn at random from the space of keys. And that is something we've seen often before, but then comes something novel, and that's a return statement. The return statement on K means that the adversary actually gets back this key as an input. The key is not secret. There is a key, but the key is known to everybody, including the adversary. There are no non-trivial oracles. There's no exported procedure other than initialize and finalize. What the adversary does is, given this key k, it asks itself, how do I find a collision for the function h sub k, 2 points x1 and x2, such that h sub k has the same value on them. It trundles along. Whenever it thinks it has the answer, it outputs it, or if you like, calls finalize with the pair. And the job of finalize is to check that the adversary got it right. So how does it do that? Well, fundamentally it checks that if you apply h sub k to x1, you get the same thing as if you applied to h sub k of x2, and it returns Boolean true or false, depending on whether that holds or not. There's a few auxiliary checks. For example, make sure that the inputs are different, otherwise you have a trivial collision. If they're the same, then the game says, sorry, you don't win. It should usually be understood that any inputs provided by the adversary are in this set D. It doesn't make sense if they're not. The function isn't even defined there. For completeness, I put that in the game. So the game checks that the inputs are in the set. If either of them isn't, it also says you don't win. This adversary then has some chance of returning a collision, and hence there is a certain probability that the game returns true when executed with it, and that becomes the adversary advantage. As usual, the superscript is the name of the metric, collision resistance. The subscript is the family of functions of security we're measuring, and the argument is the adversary. So now we know how we want to try to measure security of hash functions. This is mainly text to restate in writing what I stated verbally, and its purpose is to ensure that if you go back over the slides, you have something to remind you about the different conventions. Some of these conventions are new and important, and one of them is that initialize as a return statement, and that means that the adversary is handed the key and it's not secret. Let's try to exercise the definition and also, as usual, build up our attack muscles by finding collisions in some kind of example function. So let's fix a large number n, like 2 to the power 256. And I'm going to define a function. The space of keys is all integers from 1 up to n. So there's 2 to the 256 keys. The domain is actually all integers. So the infinite set of non-negative integers. And the range is all numbers between 0 and n minus 1. The function is defined on input key k and input value x to simply return x mod k. So x is an integer, you take it mod the key, which is also an integer, and you get back something in the range 0 to n minus 1. So our question is this collision resistant? Well, you know what that means. It means that you're asked, can you design an adversary playing the game we just saw and achieving a high advantage with very little work? You can play with this a little bit, but you'll soon see that the answer is no. It's quite easy to find collisions. One simple reason is that adding k into an input doesn't change the output. K mod k is 0, so if x plus k mod k is the same as x mod k. In other words, the value or output of the hash function on input k and x is the same as on input k and x plus k. The addition here being performed over the integers. If this comes up in homework or a quiz, you will usually be required to write an actual formal adversary. So the attack would be specified as a pseudocode or Python playcrypt adversary. This adversary has a certain syntax, and it's important to respect that for meaningfulness. And this showcases a few new elements. So we notice that the adversary now has an input, and that input is the key. Why is this? Because according to the game, initialize returns the key, and our convention is we write that as an input for the adversary. This is pretty important because this adversary uses the key to find its collision. It picks one point arbitrarily, but the second point is supposed to be that plus the key. Luckily, it knows the key, so it adds 0 to k to get the second point, and it just returns them. Returns means they become the inputs to finalize, and certainly finalize looking at these two, we'll see that everything checks out. They're not equal to each other, and also the value of the function on these two is the same. So our adversary has advantage 1, and we've shown very conclusively that this is a lousy hash function as far as collision resistance goes. Here's another example where we tried to do better by exploiting existing cryptographic mechanisms. It may have been too much to hope that we could design a secure collision-resistant family of functions just by a little bit of mod operation and nothing else to go from. But we have a lot to go from. We have, for example, block ciphers. Why don't we exploit those to build hash functions? So here I'm assuming I'm handed a block cipher with k-bit keys and n-bit blocks. I assume it's, let's say, PRF secure. I'm trying to build a hash function which also has k-bit keys. It takes two n-bit outputs and compresses them down to n-bit outputs. It says two n-bit inputs to n-bit outputs. So how do we do this? Here's pseudocode for the function. It breaks its two n-bit input into two blocks, each n bits long. It runs the block cipher with the key here on the first block. That gives it some n-bit string. XOR in the second block, so another n-bit string, apply the block cipher again with the same key, and that's our output. Fine, so it's some sort of design, and we are going to show that for as far as collision resistance goes, it doesn't work. This claim is true regardless of the block cipher. No matter how secure a block cipher you had, or what PRF security it had in particular, the hash function fails to be collision resistant. There's always going to be an adversary that achieves advantage 1 in the collision resistance game. So how do we do that? When we're giving attacks as usual, we start with a little bit of intuition. We're trying to see how someone could come up with two inputs which make the output of the hash function the same, the key being the same in both cases. So this comes down to some kind of equation solving. What you do is you have to find two inputs. Remember, each input is two blocks long. If I have one input x1, it'll be like this. The other input x2 will be like this. The result of the hash function on them will be e sub k of the first block plus the second and another e sub k. I want those two things to be equal. I notice, however, that if I could just make these equal, which is the first part here, and ignoring the last e sub k, I would be done. Because if already these are equal, applying a further e sub k will leave them equal. So to find a collision, it at least suffices to solve this equation. What does it mean to solve it? Well, we are handed the key k. That's not up to us. But in fact, everything else is up to the attacker. It can pick x11, x12, x21, x22. There's 4 choices it can make. And it just needs to make them to make this equation true. And there's multiple ways to do that. But the adversary shown here has chosen one such way. This is another maybe a good general point with regard to writing adversaries. Your adversary has to be a specific piece of code that compiles properly. And so you need to make specific choices. This one takes x1 to be the string whose first block is 0 and second block is 1. And x2 to be the string whose second block is 0. And then it looks at the clever part, which is how to compute the first block of x2. How does it do that? It looks at this equation and says, having picked this arbitrarily and this arbitrarily, and also picked this arbitrarily, I'm going to solve for x21. Why is that possible? Because e sub k has an inverse, ek inverse. So I can solve for this by applying ek inverse to all this plus this. Importantly, I can only do that because I know the key as the adversary. If I didn't have the key, I could not compute e sub k inverse. But as it is, I do that, and this is the formula for it. And since this equation is satisfied, the 2 points returned are a collision. Make sure your adversaries are syntactically correct. They take a key as input for collision resistance. They return a pair of points. These have to be in the domain. So this attack used quite crucially the fact that the adversary knows the key and that E is a block cipher so that you can invert if you know the key. And but you might try just for fun to find another attack which works even if you don't know the key. So does that mean that starting with block ciphers is not a good way to build hash functions? Not necessarily. Maybe there are other things that work. So here's, for example, is an attempt that's more involved than the one we had. You do start with a block cipher, but you use it in a slightly more involved way. But the purpose of this exercise is still on the attack side. It shows you that you will be able to give an adversary violating even this one. And that raises the question of how we are in fact going to do better. We spoke in general of hash functions as being a syntactic object that's a family of functions. So it has two arguments, a key. Even though that key is known, it's still a key chosen at random, and an input in the domain D and an output in the range R. But practical hash functions like the MD and SHA series are in fact keyless. So we can capture that if we like formally by thinking that there is a space of keys, but there's only one choice in it. And formally we could imagine that choice to be the empty string. When that happens, we'll drop the key argument. So we'll just write h of x in place of h of either empty string in x or h sub empty string in x. And this will come up when we look at these practical hash functions. So remember where we left off is that we actually didn't have any example of a hash function that did satisfy collision resistance. We hadn't been able to find one. So how do cryptographers get these things? Well, they're in the same category in terms of primitives as block ciphers like DES and AES, in the sense that cryptographers build them from scratch using a combination of various bit and arithmetic operations, iterations for a certain number of rounds, and other ingenuity, and eventually establish to the best extent possible their security through examination and cryptanalysis. So just like we looked at the design of DES, we'll look at the design of one popular hash function, which is SHA-256. This is in quite widespread use now that SHA-1 has been dropped out. And this will show us, as with block ciphers, that all kinds of things happen, and we don't necessarily know in all cases why they happen the way they do. But also there is in fact a fair amount of high-level structure and some set of things that we will be able to study and understand in quite amount of depth. Okay, so SHA-256, the hash function, takes very long inputs. Technically, what this means is that the input is any bit string whose length is less than 2 to the power 64. Given, however, the 2 to the power 64 is just humongous, in practice, you can just think of it as taking strings of any length. It's a keyless function, so you won't see any key arguments appearing anywhere. And the output is 256 bits long. So let's start looking at the design. It takes an input x, a string of very large length. The first step is to pad x. We can look at the details of the padding at some point, but the purpose of it is to ensure that the message M here coming out has a length that's a multiple of 512. That allows us to break M into 5 12-bit blocks as done here, and that's because we will be processing it block by block. Next, some constants are defined. So we set H0, H1, and H7 up to H7, 8 of them, and the superscript, because more such things are coming, to be various fixed constants. We now collect all those up. Each of these things has length 32, and so this string here has length 8 times 32, which is 256. So it's set up to have the same length as the output of the hash function. Next, there's a loop. What this loop does is it eats up one message block at a time, and it processes that message block with the aid of some auxiliary function written like this. This is called the compression function, and it takes an input of length 512 here plus 256, and it gives you a 256-bit output. So you apply that to the first message block and to this constant H0 that we created here. That gives you H1, which is 256 bits. In the next iteration, you take the second message block and the constant you created, H1, you created before, and you compress them down to H2 and so on. When you're done, you return the last H value, which is denoted like this. This high-level structure is pretty clean and elegant, and more than that, we'll later be able to see that it's sound in some sense. It's provably good. But as far as understanding the function goes, we now notice that pretty much the work is in here. We do have to also consider there's a subroutine here, but the bulk of the cryptographic work is going to be inside this, and so that's the object of interest. Before we get there, we can look at the padding function. So what's its goal? Again, remember, it gets a string x of some arbitrary length, and it's got to produce a string of length, a multiple of 512. The way it does that is that it takes the original string, it puts a 1 bit, and then it puts the length of the resulting string m expressed in 64 bits here. It then picks d so that this whole thing has a length which is L and is a multiple of 512. So that's the padding function. Another question that arises here is how exactly were these constants chosen? Why are they the values written over here? And it turns out that they obtained those values by some sort of arithmetic where they took the first j prime numbers, so 2, 3, 5, 7, 11, etc. And then they took their square roots, looked at the fractional part, and looked at the decimal expansion or whatever, turned it into binary and took some bits of it. So some way to create some values that are random looking, but also algorithmically determined. It's an interesting question as to why do this at all? Why should we use these square roots to pick these constants as opposed to just picking whatever and embedding it in the code? And it's not clear any public reason was provided, but one possibility is that there is suspicion of subversion, meaning the entities that design the algorithm have built-in constants that aid them to break it because of some properties they have, but are not known to others. And this ensures that that kind of subversion hasn't happened. It's been done by some kind of random looking but well-specified process that someone can repeat. Okay, so now next step is we need to look at the compression function and see a little bit how it works. So remember, it takes an input of length 512 plus 256 and returns an output of length 256. So 768 bits to 256. So its input is broken into two parts, the 512-bit message block and what's then the 256-bit value, V, which we usually refer to as a chaining variable. So how does it work? Well, we had earlier considered that we want to use block ciphers in some way. It's natural to do that because block ciphers are things that we've worked on a lot and people think they know how to design. And indeed, the compression function here relies on a block cipher, but not a block cipher we know. They have their own block cipher, which is called E-SHA-256 up here. And it takes a key of length 512 and an input of length 256 and returns a 256-bit output. Once you run that block cipher on this key and input, you get a 256 output. You break up into 8 32-bit words. You also break this 256-bit string into 8 32-bit words. And then you add correspondingly here to get these little h's. This addition is done modulo 2 to the 32. It's not XOR, it's addition of integers mod 2 to the 32. You then concatenate these results, and that's your final output. So there we have it. In fact, even this step is quite elegant. and we'll be able to later give a fair amount of understanding of why it works the way it does. So where is the heart of it then? Well, it would be inside this E actually. So it's the block cipher that contains the bulk of the cryptographic processing. And that is much more complicated. So that we won't look at in detail, but I've just kind of put down things here to give you a rough idea about what goes on. You have a 512-bit key and a 256-bit input. You need to produce a 256-bit output. You start by breaking the key into 32-bit words, and then you assign these working values as to start with to these key blocks. And then you start applying transformations that start mixing these up. From these original 16 WT words, you go and define a whole lot more so that in the end we have 64 of these 32-bit words. And the others are obtained from the initial ones or prior ones by applying various functions that we won't necessarily discuss in detail. You take this 256-bit string, break it also into 32-bit words, and then initialize a state. And this is done by setting different parts of the state to these initial values. Block ciphers always operate in rounds. The rounds are crucial towards getting security. So now what happens is that you take the current state and you iterate on it through 64 rounds. And that iteration will depend on the key entering through W, and then also on of course, the state that's being changed, and it uses various functions inside and so forth. In any case, at the end of the 64 rounds, you take your current state and you return that. So we're not going to, in these slides, detail many of the functions that you saw in the code earlier. But these are all public functions. You can find a description of SHA-256 at many places on the internet. And if you're curious, you can always go and see what these functions look like. Maybe worth commenting again that the C values that we saw here, like here, are in fact further constants. And again, they're obtained by that same sort of method. Here they look at cube roots rather than square roots of prime numbers, and then start taking the fractional bits. If you want to play with SHA-256, you can code it up, or you can even go on the internet and pull up a hash function calculator, and online you can type in some text and press the button and it'll give you the SHA-256 result. Not much to look at there, it just looks like some sort of gibberish. Let's turn to thinking about what hash functions are good for. In particular, why would we be interested in collision resistance? So the killer app is certificates, in particular the use of hash functions in digital signatures, which are then used in certificates. And that, however, to study requires us to know what signatures are, and so hence it'll be postponed a little bit. There are also other uses like data authentication with HMAC, but for that we'd have to be studying MAX, which is a little bit further down the line. So at least for a starting point, I'll just illustrate something much more direct, if you like. So, which is how you authenticate yourself with a password. So this is something we do routinely. Every time you log into Gmail or many different websites, what you do is after having contacted the server, there'll be some sort of page in which you enter your login name and password, and that authenticates you and lets you access the service. In settings like this, what's happened is that the client has a certain password which has been chosen at some point, and it's stored on the server. And then what the client does is it sends the password over to the server whenever it wants to log in, and then the server says, oh, okay, I'm going to check that against my local copy, and if you send the right password, I think it's really you, and I'll let you in. Now this would be pretty silly if we just sent it over the clear in the internet, but the way this is done is over a TLS channel. So for example, when you log into Gmail, you already have a connection secured by the server's certificate, and everything sent over is already being encrypted with a session key. So the password is not going in the clear. Now, that setup is fine, except that there's a weakness arising from the fact that it seems fairly common and routine these days for servers to be compromised. So server breaches are weekly news, and large amounts of sensitive information is exposed by them. Amongst the possible information that could be exposed is passwords. If your server has a bunch of passwords on their website, there's danger an attacker would simply discover them that way. Due to that threat, what we just saw is not how password-based authentication is done. Instead, what's stored on the server is not the client password, but a hash of it. So a hash function like SHA-256 is applied, and the server stores only this hashed password, which I'll denote by PW with a bar on top. How does that change the authentication mechanism? Well, over your TLS channel, when you want to authenticate yourself to the website, you actually still do send your password. You send your password over in the clear, and it's not really in the clear because it's over TLS, but abstractly from our perspective here, and from the perspective of the server, it is in the clear. The server gets it, computes the hash function is public, and checks that it matches the stored hash. And if that case, it says, okay, you're who you claim you are. So now the reason to do this and the expected benefit is if an attacker compromises the server and gets a dump of all these values, there's much less there that's actually valuable. It doesn't get clear text passwords anymore. It gets password hashes. And if your hash function is good, it is hopefully the case that you cannot reverse the hashing to recover the original password. And note, you need the original password in order to successfully impersonate A. Just knowing the hash isn't enough to do that. Well, collision resistance turns out to imply one-wayness, and one-wayness is the property that says it's hard to reverse the hash function to get the password from the hashed password over here. And so we see some kind of meshing with the properties we've been defining. Now, from the point of view of motivating hash functions, that may be a fine story or stopping point. But the fact is that if you're actually interested in security for password usage, there's a slew of further problems, and it would be inappropriate to somehow not make that clear. The difficulty is that passwords are often poorly selected. And because of that, when you have a hashed password, it's often quite easy to recover the original one because you just try a certain set of candidate passwords from a relatively small space. And this compromises many users of passwords. Well, nonetheless, all that taken into account, this is how client authentication is done on the internet, meaning you flow your password over a TLS connection and the server has the hashed password. So we have now seen an example of a hash function and some idea of how they're used. What can we say about security? So let's think about how hard it should be to violate collision resistance for a hash function. Now, certainly from the examples we've seen before, it's clear that it will depend on the design of the hash function. If you have a bad design, it may be very easy to violate collision resistance, and if you have a good one, it may be a lot harder. It turns out, however, that there's also a generic attack, meaning that there are some intrinsic inherent limits to how much security you can get under collision resistance due to the birthday attack, which finds collisions in any hash function. Of course, it needs a certain amount of effort, and the takeaway is that the effort is about the square root of the size of the range. The range here is n-bit string, so there are 2 to the n points in the range. This is the square root of that, which is 2 to the power half of this n over here. The takeaway from birthday attacks is that when you are willing to invest this much effort in terms of computing time, you can in fact find collisions. The response is simply make this number large enough that this is prohibitive. But it's certainly nonetheless interesting to see how it all works out. So let's see, how would you find collisions in a given hash function by exploiting the birthday paradox? So here's our adversary. It's subscripted with Q because we parameterize it by the number of trials or the computational effort that the adversary is willing to invest. And we'll see that its advantage grows with however much that is. Remember that as a CR adversary, it gets the key as input and is trying to find collisions in H sub k. H is a public function. Everyone knows what it is and how to compute it. The adversary doesn't have any oracles or anything. It just performs computation. So what does it do? It first hashes a whole bunch of inputs, Q of them, and gets the corresponding outputs. And how does it pick these values? In this case, at random. It wouldn't particularly matter, but it picks random domain points and gets Q outputs. And then it just sees, did I get lucky? Somewhere in those outputs, does a collision occur? Meaning, can I find two outputs that are equal to each other, even though the corresponding inputs are different? If that happens, the corresponding inputs form the collision. If I return this finalize of the CR game, we'll look at it, compute the hash function on each of them to get yi and yj respectively, and notice that they're the same and say, okay, you win. And that's it. That's what the attack looks like. What's interesting about it is that you might not think at first that it's very effective. And what makes it effective is the birthday paradox. Even though the effort is proportional to this parameter q, the success probability is proportional to q squared. And that's where the power of the attack comes in. So the birthday attack analysis shows that, at least for most hash functions, the adversary advantage is at least q squared over 2 to the n up to some constants. And that's how we get this conclusion that you need about 2 to the n over 2 in the exponent trials to find a collision. What does this mean for actual hash functions out there? Understanding that this was the attack method and metric led people to carefully choose the output length of the hash function, and as computing power grew, to also keep ramping it up. MD4 chose an output length of 128, thinking that making the birthday attack take time 2 to the 64 was good enough, that's prohibitive enough that people aren't going to find collisions. And the same with MD5. By the time SHA-1 was designed, they were more conservative. They said, well, 2 to the 64 effort may be feasible. Let's try to make sure that the adversary has to work this long to find collisions, so let's make our output length double that exponent. And it kept going up. SHA-256 was created with this output length so that finding collisions takes this much time, and it can ramp up further even than that. Given that this attack is unpreventable, the target in hash function design is viewed as being make sure nothing better works. That we should design the hash function so that no attack better than the birthday attack is possible. What we'll see, interestingly, is many of the early hash functions fell short in that regard. Before going on with further hash function technology, I thought I'd just step back to reinforce the point about passwords and their choices. It came up in a sort of peripheral way in our description of an example of how you use hashing, but it's kind of fun to look here to see the threat from looking at choices of passwords and which are the most popular passwords. So this is a list of top 25 most common passwords by year found by some data gathering company. And the risks are pretty obvious. Look at this. So in 2019, the most common password is 123456. And that was true for the last 5 years or so before that. Earlier, there was simply the word password. For some reason, this has switched around. So in these years, 123456 was most popular, and then password was second, and then it switched in more recent times. And you can look here and you can probably explain most of these choices. This is the keyboard letters. Sequences of digits are very common. I love you and dragons, monkeys, baseball, whatever. So as long as people are choosing passwords like this, dictionary attacks are going to be very successful, something worth remembering.